All right, so let's get started. So last time we talked about how if you were to think of a black hole in terms of quantum information carefully, and you study the evaporation process, then you end up with a situation where the black hole becomes maximally entangled with the early radiation, and then you had this monogamy problem, monogamy of entanglement, and hence the firewall paradox. So that argument relied on having the black hole be maximally entangled with the early radiation, and some of the questions were about what about young black holes that are not maximally entangled with some radiation? Are there any arguments that cast doubt on the existence of the interior for those situations? And that's what I'm going to talk about today. What we're going to consider is black holes in ADS, in particular large black holes. Let me review that briefly. So we want to consider large black holes in ADS. So what makes them large? Physically, it's the following property, where you can consider collapsing a small shell in ADS or a large shell in ADS. So if you collapse a small shell, by small I mean a small amount of energy, then you can form a black hole which as we said radiates, and you can end up with a situation where it radiates away completely. And you're left with just gas in ADS, versus the situation where you insert a lot of energy, and therefore, before the black hole evaporates, before it evaporates away completely into radiation, the radiation gets reflected off the boundary and falls back into the black hole. Therefore, the black hole comes into thermal equilibrium with its radiation. And in these situations, by studying carefully the number of states of black holes and the number of states of possible radiation in ADS, you can convince yourself that you can show that the number of states of the radiation is much smaller than the number of states of possible black holes, assuming the energy is large enough. And so in this situation, because the state is in a pure state, it's not the black hole that is maximally entangled with the radiation, but the radiation is maximally entangled with the black hole. So in some sense, it's like a young black hole in flat space that just began to radiate. So the key features of these black holes is that first, they're stable. As I said, they're in thermal equilibrium with their radiation. Second, the number of states of these black holes, I'm going to call that the dimension of the Hilbert space at some energy E with some small width, goes as the exponential of the Bekenstein-Hawking entropy of these black holes. Some of you have heard of the Hawking-Page transition. Here I'm considering energies that are above the Hawking-Page transition in the microcanonical ensemble. Okay. And the question now of whether there's an interior or not can be rephrased as the following. So in ADS-CFT, we want to understand the dictionary between the bulk and the boundary. For any operator in the bulk, what does that correspond to on the boundary? And the question we want to address is, what is the dictionary for the mode B tilde behind the black hole horizon? Because presumably, if we know the dictionary for this operator, and let's say we also know the dictionary for this operator, which we do, then we can just, in principle, compute and see if B and B tilde are in the correct entangled state. So the question is, what is the dual of B tilde? Yes?
Do you assume a semi-classical approximation in the black hole interior?
You begin by assuming that, and then you try to find the contradiction. Okay. Anything else? Okay. So let's begin. The first problem is called the transplanting problem. It's not a paradox, but it just shows that the dictionary for the interior modes is something non-trivial, and it's hard to arrive at. So to begin, let me just review an important piece of the dictionary of ADS-CFT, which is that near R goes to infinity, so near the boundary, we have what is called the extrapolate dictionary. So and the limit is R goes to infinity, R delta, phi, some bulk field, bulk operator, Tx is identified with a local operator, T comma x. So phi has some fall off that goes as R to the minus delta, and you strip that you strip that fall off factor off by multiplying by this. And we can use this dictionary to find what B is dual to in the bulk. So you can do that simply by evolving B forwards. Can you guys see this? Good. By evolving B forwards until it's very close to the boundary, and then you use that formula to find OB, and then you can evolve it backwards in time if you want to know the expression of the operator at different times. If you try to evolve B tilde forwards, well, it's just going to crash into the singularity, and so it's not going to make it out to the boundary. So that doesn't work. So the only possible thing you can do is evolve backwards. Now, something which I ignored here is the fact that there's a shell which formed the black hole. Okay, so now naively you might say, okay, let me just evolve backwards. Well, this is going to go back, get reflected off, this is R equals 0. This is R equals infinity. Get reflected off R equals 0, and then it'll go all the way to the boundary, and there you go, you can find OB tilde. So maybe I should draw it again here. So there's a shell, and there's B tilde. So naively, you might have said that I can just do this. And now I can find OB tilde. Except that this is too naive. We need to take into account this interaction. In particular, if you start with a B tilde late enough and evolve it backwards in time, it gets more and more blue shifted. So it gets blue shifted to the point at which this scattering between B and the shell becomes transplankian, and we know what happens in such collisions. You form black holes. So the physics is CPT invariant. I can evolve backwards, and this is a collision that forms a black hole. And so what happens is that you form a singularity backwards in time, or you form a black hole backwards in time, or said differently, you form a white hole. And B tilde again crashes into the singularity. Yeah, and so it seems like you cannot take B tilde close to the boundary to use the extrapolate dictionary, and therefore you need another set of ideas to find the dictionary. Now I should say that For B tildes that are close to the shell, then this is not a problem because the blue shifting is not large enough for this collision to form a black hole. And for that case, you can evolve it backwards in time. But what is interesting for us is the operators at late times. Yes?
So the B2 could be produced by the fluctuation around the horizon. So why can you evolve back even before it's created?
Well, I mean, you can just no. You can imagine. So let's say there exists an OB tilde. You know that if you acted on this time, it should create something here.
Yeah.
So I'm creating it, then evolving backwards.
Okay.
Yeah. Any other questions?
So can you just repeat the argument how you form the white hole?
So I'm evolving backwards in time, and this is a collision between B and the shell. And the physics is CPT invariant. I mean, you know that if you collide two very high energy shock waves, you'll form a black hole. But it's also true sort of backwards in time. If you have two high energy shock waves and you're evolving them back, they collide, they'll form a white hole. That's the idea.
I just asked the teacher that you cannot act on O in the late time to create the feature.
Why not?
Inside
I mean, if there's a dictionary between things that I can do here and things that I can do on the boundary, then I can do it. Okay, so again, this is not a paradox. It just shows that the dictionary for B tilde is non-trivial. All right, the next argument is a paradox. It's called the B tilde dagger inverse problem. Okay, so draw a black hole again. We need to invest in a stamp that just stamps black holes. Okay, so consider the operator B tilde dagger behind the black hole horizon. Because the killing field, so at late times, the Hamiltonian, the CFT Hamiltonian generates the following killing field in the bulk. It looks something like that. On the exterior, some time-like vector, but in the interior, it's a space-like vector. It looks like that. This implies that the commutator of the Hamiltonian with B tilde dagger is equal to minus omega B tilde dagger, assuming that B tilde dagger creates a mode of frequency omega. The point here is that this is negative, so it lowers the energy. And just for to get intuition as to why this happens, in the case of a black hole evaporating, recall that assuming the Hawking process, you have these modes B that go to infinity that carry the energy away. But now to make the black hole actually get smaller, the modes B tilde behind the black hole horizon must lower the energy of the black hole. So as the black hole is getting smaller by creating more B tildes, the energy is now being carried out to infinity by the B's. Not B's, but by the B's. Okay. The intuitive argument or this argument? Well, this argument is you need to keep track of details of the wave number of the mode, but because the killing field is space-like behind the black hole horizon, it is time-like outside. Okay, this means that if we consider let's see. Again, we're considering some microcanonical ensemble at some energy E. And so I'll define this again as HE, which is what I wrote down there. So we have that, so if we label the states as I belonging to HE, we know that the dimension of HE, as I wrote down previously, is just a Bekenstein-Hawking entropy at this energy. But now you can consider the set of states that you obtain by acting on these states with B tilde dagger. Okay? These states, because B tilde lowers the energy, it's in the Hilbert space HE minus some DE, determined by this frequency and the temperature. And the dimension of this Hilbert space is roughly e to the Bekenstein-Hawking entropy minus, using the first law, dE over T. Okay? Where this thing, I guess you can write it as beta omega. Beta is 1 over T, and omega is the energy that this mode lowers the system by. But this means that, B tilde dagger annihilates an order e to the minus beta omega fraction of states.
Sorry,
Yes?
your formula last one, e to the s dh minus d over d, is
Yeah.
what? It's the dimension of this space in a certain game?
It's a dimension of the space that you end up with by acting on all of these states with B tilde dagger. So it lowers the energy, so necessarily brings you down slightly. Maybe I'll just, that's HE minus DE. Okay, so it looks fine. So I mean, this doesn't seem like a problem, except, but B tilde dagger actually has a left inverse. So consider the following operator: 1 over 1 plus B tilde dagger, B tilde times B tilde. If you act this operator on B tilde dagger, you get the identity. So here's where the assumption of having semi-classical physics comes in. This is a relation that you can derive from just QFT on a fixed background. Well, yeah, I mean, it's obvious. It just follows by the algebra of B tilde and B tilde dagger. Yeah, but these two statements are in contradiction. You can't have a left inverse and at the same time annihilate some states. Any questions about that?
The fact that B tilde dagger is the same as the denominator over there? Is the same as 1 plus B tilde dagger B tilde?
That's right. That's right. I'm assuming the usual quantum field theory algebra for raising and lowering modes. Any other questions? Yes? Say that again? Oh, good. I mean, you can choose omega to be of order the temperature. And then this fraction is of order half. No, the temperature is 1 over m, the m being the mass of the black hole. I mean, which is a very small temperature. So B tilde doesn't really create anything which back reacts significantly on the geometry or anything. The temperature is like 1 over m.
But this is a,
Oh, no, sorry.
it should be range.
Yeah, but it's still small. That's right. Thank you. Any other questions? Okay. The next and final argument is the typicality argument. So
Sorry, the essence of this argument is that since B tilde dagger is behind the black hole horizon, it lowers the energy.
yes. If you try to apply the same thing for B outside the black hole horizon, there's no problem because B raises the energy. And so you know that it does not annihilate any states. Sorry, B dagger. Thank you. Yeah. Thank you. It doesn't need to annihilate any states. Yes, yes, yes. Somebody had a question. Yeah?
How does the gravitational Gauss's law work in the presence of Bichilda particle?
I mean, secretly, I'm using the gravitational Gauss's law. I'm saying, by saying that it lowers the energy, means I took that into account. Yeah. I mean, everything here is dressed to the boundary, and that's the thing that registers the energy in the bulk. Okay. So next is typicality. So for this, we say, again, we consider this microcanonical ensemble, and we say, let's compute the average of NA in this microcanonical ensemble. Let me remind you what A is. So we have the B tildes inside the black hole. We have the B's on this side of the black hole, and we also have the A modes, which you can think of them as the modes living on the horizon. And we had a relation between A went as B plus some factor B tilde dagger, something like that. So yeah. And so the statement of, for example, the statement of saying that there is no drama is a statement that the state is annihilated by NA. And recall, this means that the only such state where this is true is the thermophile double state of B and B tilde. Okay, so now let's compute the expectation value of NA within this microcanonical ensemble. Well, this means we just take the trace within this ensemble of NA divided by the trace of the identity operator as a normalization. Now, recall that we understand the dictionary of B on the boundary, and it's some, well, NA, sorry, NB. We understand what that is on the boundary. It's some Hermitian operator. And we can choose to evaluate this trace in any basis we want. In particular, we can choose a basis of eigenstates of the NB operator. So by that I mean states of the form n, I, where this is equal to n, I. So you should think of this register n tells you what the occupation number of B is, and I is all other information about the state in the CFD. So this is a basis that we can use, and therefore we would write.
Assuming that number operator commutes with the Hamiltonian.
Sorry, which number operator commutes with the Hamiltonian?
NB.
Oh yes.
Because you're taking
That's
a
right.
trace over the subspace of states in a narrow energy band, and so if you want to say that has a basis of eigenstates to the NB, you better commute with the Hamiltonian.
That's right. So I'm making the assumption that NB Hamiltonian within this ensemble is roughly 0. Good point. Okay, so now we can just, so this trace evaluates to, well, we can just write this in terms of this basis. And so we have N, I, N, A, N, I, divided by this normalization, which I'm just going to call 1, trace 1. Now, as I said over here, the only state in which NA is equal to 0 in is the thermal field double. In particular, for any product state for B and B tilde, or for any eigenstate of B, then the expectation value of the number of this thing is order 1. And therefore, this average is also order 1. So it's, and so on average, you find that the number operator is, that the number operator for the A mode is occupied. Now you might worry that maybe what happens is that there are a few highly excited states of NA, but the typical state has 0 expectation value. So if within this ensemble, most states have expectation value NA equals 0, but a few of them have very high NA, then you can still satisfy this. But you can rule that possibility out by instead computing the trace average of 1 minus P naught, where P naught projects on the state where NA is equal to 0. So projects on psi where n psi is equal to 0. But I'll leave this as an exercise. You can convince yourself that this is almost 1. So this says really that it's not just a few states that have high occupation number, but it's really sort of most states. Any questions about that argument?
Well, when you say it's all 1, is relative to what? There's a coupling constant somewhere?
I mean, you have, for example, the central charge of the theory. It's not like 1 over n or anything like that. Yeah. Okay? Which is controlled by the central charge. That's the, yeah. Should be more precise, I guess. Yeah. So it's not something where, you know, in the semi-classical limit, as you take c goes to infinity, it would go to 0.
You assume that the Hamiltonian commutes with the number operator for tilde particles?
No, nothing here assumed that. Here it's just that it commutes with NB. I didn't make any statement about B tilde. Okay? So these were the 3 other arguments for a paradox / non-triviality of reconstructing the interior. Now I'm going to talk about the counter proposals.
Sorry, why is it contradiction? Why
So this is not a contradiction. It's just saying that it seems like firewall states are typical in the Hilbert space. Yeah. Okay. Okay. The first counter argument I'm going to talk about is so after my talk last time, I was asked about what happens if we relax postulate 2. So this was postulate 2 was a statement that that the physics outside the black hole, outside some stretched horizon, is controlled by semi-classical field theory. It was a statement that BI evolves to BF, as in BI is equal to BF. Oops. That was postulate 2. But now let's relax that and say that they're not equal. And so this goes under the name of nonviolent non-locality. Oops. Of Steve Giddings. Okay? And it comes in two flavors. The first is what we called a non-local swap. Which goes something like this. So say you start with the state of the black hole, I H prime, J H. So the dimension of H prime times H is equal to something like e to the Bekenstein-Hawking entropy. Here I did a division where you should think of this register H as the next bit that the black hole is about to radiate. The idea is to say that the way the Hawking radiation goes about is that there's a first step before this information escapes to infinity, in which you append to this state an auxiliary state k of b tilde b. So b tilde b. So you append an entangled state of b tilde b. You should think of this as the thermal field double of b tilde b. So you have, here is b tilde b. And as b is evolving away from the black hole, it goes there. I'm going to need to erase some of this, actually. I can do it here. Okay. As b is evolving away from the black hole, there's a swap that happens. You swap H and B. So the resulting state is the following. Sum over K, I, H prime, K, H, K, B tilde, J, B. So J was some state of the black hole. I don't know how to represent. But then there's some non-local interaction that swapped the states, H. That swapped the states of H and B. So, so this looks good in the sense that the information has been ejected away from the black hole. It also looks good in the sense that when B tilde and B are close to the horizon, they're in the correct entangled state. It also looks good in the sense that the dimension of the black hole Hilbert space was H prime times H before the swapping happened, but after the swapping, its dimension is only H prime. You might say, well, hang on, isn't all of this also inside the black holes? Shouldn't I also take those into account in counting the number of states of the black hole? The proposal is no, you shouldn't, because it's always in the same state. It doesn't matter. It doesn't add any information to the black hole. So really the black hole Hilbert space here is spanned by this factor. Except,
Sorry, so does that mean if I put it in a different state and I evolve back, I get something that's not a black hole?
hang on. That's what I'm doing here. So the so say that again. What's the?
What is H prime? Where is the H prime?
Oh, I mean it's. So I mean it's. I mean I don't know how to write it here in the diagram, but the black hole Hilbert space at this time slice is spanned by H prime and H. So the dimension of H prime times dimension of H is equal to the Bekenstein-Hawking entropy.
So what is little h?
Oh, I made this. So what I said was I made this separation into H prime and little h just to emphasize that this is the next bit that the black hole is about to radiate. I mean that was it. There's nothing special about this. It was just a convenience.
And you ignore the radiation Hilbert space.
Yeah, I don't care about the radiation. I don't care about the radiation. You can imagine this. I mean, you can add the early radiation. You can entangle it with this, but it's not going to add anything to the discussion.
So you mean small h is the mode that will radiate off sometime later?
H has the information that is going to be radiated later. Yes. I mean, it's not literally the mode because the mode is B. I mean, that's the mode that went away, but the information from H has been deposited in B, or there was a swap. Okay? Yeah, but there is a problem, as Daniel sort of alluded to it, is that before the swap happens, you can imagine interacting with B. You can send what is called sort of mining apparatus, essentially just send something in that modifies the state of B. For example, you can consider the situation where you act on B with a unitary to add a phase factor, like the following. Here's a phase factor, KB. So one can do that. And then let the swap happen. And so you get some K, I, H prime, minus 1, K, H, K, B tilde, J, B. So again, the information about H has been released to the Hawking radiation. Before you did the interaction, the horizon was smooth. I mean, it's okay for you to do an interaction after B sort of escapes. That's no problem. But there is a problem with this state when you compare it to this state. Recall that we said that we can ignore the factors H and B tilde and just take into account this factor in counting the number of states. But now it seems like we can actually change the state of H and B tilde, and therefore we've effectively, in this case, doubled the number of states of the black hole. So after the swap happens, depending on whether or not we did the interaction, we now have a black hole whose mass decreased, but whose number of states, well, in this case, depending on what the dimension of H is, increased or stayed the same. Okay, so the problem here is that you can overfill the black hole. Yes. Say that again?
What's K? Is that an auxiliary system, or should I?
Yeah, it started off as an auxiliary system, but you should think of it really as a state of the Hawking radiation.
But if it's not the auxiliary system, and I do consider a pair of like particle, antiparticle, and orbital, and if I do the same thing, would it still go through? Like instead of an auxiliary system, which is K big rho, KB, if
Sorry. Maybe I misspoke when I said auxiliary, sorry. Do you mean at this stage?
Yeah.
At this stage, you should really think of it as the state of the Hawking radiation. It's really something that is there. It's in B is evolving, and B tilde is behind the horizon, and so on.
Yes. Then it's not so auxiliary in the sense that at that stage, at least it's the
Yeah, it becomes auxiliary here.
very start here.
Sorry, but your new state do not
So,
like a smooth geometry, do not have smooth geometry.
sorry, which one does not have a?
I mean, the state after swap.
No, I mean after swap, I mean. No. You need to consider another pair of B tilde and B, and that will guarantee the smoothness for the next step, and so on. So you need to do this sort of step by step. Yes.
How can you tell there's no energy exchange during that interaction?
The non-local, the swap.
No, not that swap, but like when you act on B, when you change the phase,
Uh-huh.
how can you
Oh.
tell there's no energy exchange by that interaction? If there was any energy exchange, then it's still fine, like if you're adding energy.
It's by that same argument. The fact that you expect NB to commute to the Hamiltonian. And here, this phase is literally acting with e to the I, in this case, I and, well, there's a 2 pi somewhere, NB. So with the approximation that NB commutes with the Hamiltonian, I mean, there's a distant Hamiltonian here that defines whatever time, like the symmetry at infinity, and all energy is measured with respect to that Hamiltonian. This NB commutes with that Hamiltonian. So, yeah. Yes?
How are the states like doubled if they're like, because those are just like the same state of the big cluster?
Yeah, but they're not orthogonal. Their overlap is not 1. And therefore, now you have a two-dimensional Hilbert space. So this state and this state span a two-dimensional Hilbert space. And so the dimension of the new black hole, it seems like it's 2 times h prime, times the dimension of h prime. Yes? Yeah?
Why are you allowed to drop a state of the mining apparatus from what you wrote there? Or what all the extra states you see are
All right, so the question is, why doesn't the mining apparatus get entangled with the system? But I mean, there exist unitaries which don't entangle you with the system, which is something like this. I just act with this guy. I'm not doing a measurement. I'm just acting with a unitary. Okay, next, the next argument, also in this class. Yes?
We are basically assume that if the J can iterate all numbers in the black hole state, then we won't have this issue, right? Because when you switch to that, those two states are already included in the Hilbert space of the black hole.
Most of the Hilbert space of the black hole is in H prime. The size of H prime is much larger than the size of H.
I'll say, for example, the K choose 1 and 2, but if the J can also choose 1 and 2 in the original state, because you're going to sum over all the IJ as the black hole state, right? If you already include those J equal to 1 and 2 in the black hole Hilbert space, then those two does not add more state.
I'm not sure I followed. You should ask me afterwards. Okay. So the next thing, so the other version or proposal in this class is I guess what I'm calling now just additional flux. So the idea is to add an additional channel in which the black hole can evaporate, which counteracts the Hawking process. So I'm just going to call this additional flux. So I mean, the idea is to leave the Hawking process the same, and to add a non-local version, a non-local process of radiation that carries information. So the idea, so the picture is something like this. So you have B tilde and B, which are in the Hawking state, and the radiation of B increases the entanglement entropy, von Neumann entropy, or whatever it is. But then there's another process which just sort of creates these modes far away from the black hole, which I'm going to call this N for nu, which carries the information away. Okay? So the idea is that if you were to look at the sort of the page curve, this process would increase the entropy, but then in order for you to come back down, you need this process to purify at a rate faster than this guy. So you'd have something like this, and then you can reduce the entanglement entropy. But this is bad for a few reasons. The first is that it changes the thermodynamics of the black hole. I'm not going to explain how, but it seems that it's sort of clear that now you're changing the temperature of the black hole, essentially. You're adding a temperature for a new process that competes with this first process. The other objection is that it is prone to the deviousness of a Maxwell's demon. This is what I mean. So you can imagine the black hole. So here's a black hole. So there's the Hawking process. There's this mode B, and then there's the mode B tilde. So this is one of the bad processes that increases the entanglement entropy. And then there's this other process that pops out of the vacuum, out of nothing, and goes away and carries the information. Now, assuming you know the physics, the sort of the laws of physics exactly of the universe, as demons do, you can just go around with a mirror. I guess I should draw the demon on the tail. And you can reflect back all the information carrying bits. So via this process, you can force the black hole to evaporate away completely via the Hawking modes. And therefore, the entanglement entropy will continue to grow, and you'll have information loss. Okay, so that's the second argument. Any questions? Yeah.
The non-local swap is, I guess, a bit agnostic. Is non-local interaction only supposed to be non-local in space, or can it also be non-local?
My understanding is that it's just non-local in space.
So if I do a mining experiment, there's no way it can mess up the swap later on.
Well, I mean, if you know the laws of physics, then you can just wait until that time and then send in the mining equipment to play around with it, to mess up the state. Oh. You mean that the swap is sensitive to the mining situation? I don't know. I'm sure Steve must have discussed these various possible objections. But for now, I think this is enough for us. Okay. Maybe we can talk afterwards and see if we can figure this out. Okay. The next objection no, the next anti-firewall objection is by, is it raining outside? Oh, is by Daniel Harlow here and Patrick Hayden, which is titled Complementarity from Computational Complexity, or comp from comp. Okay? So the idea is so the state of a black hole after the page time well, we'll see what happens. Okay. Or maybe it's so objectionable that I should not talk about it. Okay. So the state of a black hole and the radiation at a time after the page time is some UT page times the state of a shell. Okay? We can write it in terms of the Hilbert space at this late time as something like H, B, H, H. So this is the Hilbert space of a black hole. This is the Hilbert space of the mode B that's just escaping the black hole. And then you have the state of the early radiation B. Oh, I guess I should have said that now I'm thinking of a black hole evaporating in flat space. I'm not in ADS-CFT anymore. This is of the radiation. There exists a basis transformation of R such that you can write down the state as the following. I'll tell you what this means in a second. RB, so it places, you can place the, you can organize sort of the entanglement in this part of the state to, and write down which, and place, so, how should I say this? How should I say this? There exists a basis transformation of this factor such that, well, you can write it in a way such that if you act with so this is a unitary, if you act with V dagger, you can extract from this state a pure state of B and some subsystem of R. I'll say it again in a second. I guess you guys can't see this factor. So this factor here is just chi H RB complement. And the idea is that in the original firewall argument, what an infolding observer needs to do, so let me label the subsystems. Here's B tilde. They need to pass through the early radiation and distill, now I'm changing conventions, and distill from the early radiation the quantum bit RB that by the page curve needs to be entangled with B in order for the entanglement entropy to go down. This process of extracting RB, which is just a single mode here, is acting with this V distillation. This process is called distillation of entanglement. And the point that is raised by Daniel and Patrick is that V distillation is hard to implement. And in fact, it takes a time of order e to the s, where s is the number of bits of the black hole to implement. Now it's interesting to compare this V distillation with UT page, which formed the black hole in this state, and we notice that UT page didn't take that much, that long of a time to implement. It just took beta log S, which is polynomial in the number of bits of the black hole. So in some sense, so this is in some sense easy, and this is hard. So it's interesting how to get to this state is easy, but it is hard to distill this bit from the early radiation. I know that Scott Aronson, who's somewhere here, is going to talk about how to understand the hardness of this V distillation in a precise way, and so I'll leave that discussion to him. What I'm going to talk about is an objection to this objection, which is, let me see. Which is this idea of Unruh and Oppenheim of precomputation. So I hope that objection was clear. Oh, maybe I wasn't, no. So here the objection is that it takes a very long time for you to distill the mode RB. It takes the time e to the s, but the time it takes for the black hole to evaporate away completely is polynomial in s. It's beta times s. And so you don't have enough time to distill the mode B and then jump into the black hole and see the contradiction. Okay, so in that sense you have complementarity. You cannot view all three systems, or you cannot observe all three systems, RB, B, and B tilde. Assuming you know the laws of physics, you know what the state is, and therefore you know which unitary V distillation you need to act, V dagger. Yeah. Yes, presumably if you know the laws of physics, you know the state, and therefore you do know which bit you need to extract. Okay, so now the objection is precomputation. So you can consider we can consider forming the black hole. You can consider forming an old black hole immediately. What I mean by that is you can have matter which is entangled with some reference system R. So this means that these two systems are maximally entangled. And then you can collapse M. Collapse and let it also radiate, plus radiation. Okay? So after this process, you have the black hole in the state H, and you have the mode B. So now, since M and R were in a maximally entangled state, this means that H and B are also maximally entangled with R. That means there's a distillation process you can implement on R. So V distillation and extract RB. RB bar. Okay? And now you can view all, the idea is that now you have these three systems and you can view the paradox. However, as I just said, the time it takes for this thing to implement is very long, and therefore the black hole would have evaporated away completely. Except that I didn't have to collapse the system M to form a black hole before applying the dagger of V distillation and extracting RB. Instead, what I can do is, I don't know, put M in the lower drawer in your office and implement V distillation, extract RB, and there's RB bar. And then once you're confident and you've mustered the courage to jump into the black hole, then you can act with the collapse unitary plus radiation And now you have this and you have those three systems, and you can witness the paradox. So is that clear? R before the collapse. This is in this example. This was just a reference system.
So would it be fair to say that this objection stands for a black hole that you specially engineered to be entangled with a reference system, but that Harlow Hayden could still be a valid argument for astrophysical black holes?
Yes, except that well. Short answer is yes, but well, I see. So you want to say for simple black holes, then you can avoid the paradox in this way, but more complicated black holes and so on. Except that in ADS-CFT, so you can imagine doing this, well, is that true? Hang on. Yeah, you can so you can work in the context of ADS-CFT. So you can be some lab technician, and you have your silicon sphere that simulates the ADS space. And then you can create a black hole in a very simple way of collapse of a shell. And then as it's radiating, you can extract the radiation from ADS space and just leave it there to do whatever it wants to do whatever processing you want on the radiation, extract the mode RB, and then jump in. So.
But that's not a thing you can do if you're part of the system.
Yeah, but you don't have to be part of the system in this special case.
Wait, this is a simulated black hole?
Yeah, he's saying you can pause the simulation, decode it.
No.
Start the simulation when you're done.
No,
A simulated person could jump in.
I object. It's not a simulation. I mean, you have your conformal field theory, which is dual to some bulk, and it's a physical system, and you can teleport yourself inside. And
Teleport yourself into the simulation.
well, I don't know. I just don't like the word simulation.
Maybe I can make one other comment. So,
Yeah.
So, in the end, I don't know whether this idea, what the final use of this idea is going to be, but just one comment about this precomputation.
Yes.
Is that the recollapse has to be, this collapsing unitary has to be absolutely perfect in order for what you said to be possible. So if by accident, while you're doing, so you're trying to collapse, an entropy's worth of soft photons, preserving the quantum coherence of all of them in sort of in a complete basis. And if you accidentally sneeze while you're doing that, and you throw in a few extra bits that you don't have control over, it kills the whole thing.
Mm-hmm. But I think in all the firewall arguments, you imagine you have perfect control and so on and so forth,
Well, I think
and you're not sick.
Perfect control at infinity. That's different than assuming you have perfect control while you're sitting a mile away from the black hole. So anyway, I don't know. It's a true fact. So it's
Okay.
a very unstable. Again, I don't know what the use of this idea is going to be in the end.
Okay. I'll leave further discussion on this for Scott's talk. Yes.
Compute this setup that you're describing here as the Beast dilation will be making the thermal field double. So
That's right.
Yeah, that's right.
That's right. But I'm going to talk about ER equals EPR soon.
The complexity of thinking.
Okay. The next counter proposal goes under the umbrella term state dependence. It's proposed by Papadodimas and Raju, the Verlindes, and I guess also some elements of this ER equals EPR proposal depends on this. Okay, so the idea is to think of a large black hole in ADS. So we're back to large black holes. The state of this large black hole, along with its radiation, is something like sum over n, phi n of the black hole times n b. I'm just focusing on a single mode b outside the black hole horizon. Now, we know that in order to have a smooth horizon, we need B to be entangled with a subsystem of H, or with something in H that in a very particular way in the thermal field double, which in my case is like the maximally entangled state. And therefore, the idea is to simply redefine this as being an eigenstate n of B tilde. Okay? And therefore, this state is just n B tilde and B. Look, it's the maximally entangled state, and therefore we have a smooth horizon. And therefore, one would write that the interior operator, B tilde, is simply the following. Okay, it's a lowering operator, which you can write in terms of this state as the gods like state dependence. N square root n minus 1 psi n b. Okay? This is a weird formula for an operator in that it depends on this state. So this is where the state dependence comes from. You can define the operator only after I give you the state. That's not a number. No, that's not a number. Psi is a state of HB. Yeah. Now, however, the problem is that this proposal is ambiguous in the following sense. So you can say that this state, so for this given state psi, you have, you can redefine things in order to have the infalling vacuum, but I can consider, instead of giving you the psi, I gave you the state e to the I theta n b on psi, which is which is n e to the I theta n phi n, which if we use this definition for what n for the state of B tilde to be, this would be I e to the n theta n B tilde B. This is not the maximally entangled state anymore, and therefore it's not the infalling vacuum. Except what the state-dependent proponents would say would be, no, you need to define this thing as n prime, let's call it, of B tilde. Then yes, sure, then you'll get some n prime, B tilde, and B. And so it's ambiguous. So which one is it? It seems like whatever state you have, even if you sort of put in by hand a firewall, you can always redefine it away. And therefore, this criticism goes by the name of I guess one name is the frozen vacuum. No matter what you have at the horizon, you can always redefine it to be the vacuum. Another criticism, which I don't have time to go into, is you can show was proposed by Don Marolf and Jose. Sorry, go on.
In the thermal field double itself, when we purify the thermal density matrix, there's a choice of phases that we implicitly make. Like I can always redefine the eigenstate of the second system by any theta angle I want.
Uh-huh.
So isn't this the same thing? And so why should those
No, so in that case, the different phases that you're talking about is when you evolve with the Hamiltonian on one side. That corresponds.
I'm just purifying.
You're
No.
supposed to take some state on the right and then the complex conjugate on the left. So phase cancel.
Thermal field double is a very specific state in which.
Whatever phases you want there. That's time evolution. It changes the state.
It's like the gods thought more about state dependence and changed their mind.
Quantum mechanics is much easier if you pick the basis first and then have your discussion rather than changing.
Yeah. Let me just say this last thing, and then maybe we can discuss a bit more. So you can find what Don Marolf and Joseph Polchinski called violations of the Born rule. In which you can sort of follow the steps as proposed mainly by Papadodimas and Raju, and end up with a situation that you have a state which by their definition has no drama, so no firewall, and the state in which you can act with some unitary like this and get drama, so there is a firewall, but the overlap of these states is very close to 1. And we know that, that one of the sort of prerequisites of the Born rule is that if you have states that are, say, eigenstates of some Hermitian operator, which in this case is, let's say, whether there's a firewall or not, if they have different eigenvalues, then they must be orthogonal. But here you have states with very different observational consequences that have norm very close to 1. So that's state dependence. Any comments, questions?
So then what is that an argument for? What does that take you to be? I think I've lost track of the nested reputations.
Okay. Well, I mean, this says that the usual rules of quantum mechanics don't apply. As a result of this ambiguity, you end up with this situation. Yeah, I mean, ultimately, so I mean, these days I'm actually a bit sympathetic to the state dependence proposal, except that you need to put in a bit more rules. So it seems right now just to be arbitrary, but I guess this is what Lenny Susskind is trying to do. He's saying that whether there's a firewall or not depends on this property of the state, which is complexity, which is not a linear property, except it's supposed to have physical consequences, according to him. Yeah. Okay. The last thing I'm going to talk about is question? Yes.
If your theta is small,
Yeah.
then you create few particles when acting on state psi. Psi is a black hole state.
No. I think for any theta, you form a firewall. But okay, but let's say.
Yeah, my question is, if theta is small, why do you need to have a different n prime? Because
Well, maybe for theta small, you might argue that there's no problem, but this argument holds for any theta. Yeah. All right, only have 15 minutes, so I need to talk about the last thing, which is ER equals EPR. Okay. Okay. So, okay, maybe I should.
E or R can be 0.
Okay. So there is an example of an entangled black hole with no horizon, or with no firewall, sorry. With no drama. This example exists. Consider the following convoluted introduction to the eternal black hole. So let's call this system R, which you know, so you're some observer. This is CFT, which I'm labeling R. It's in a thermal density matrix. So rho R is e to the minus beta h. And you know that it's dual to a horizon where you have the mode B, somewhere there. And you know that there's some other system, which you call L, that purifies R. And therefore, you know that B cannot be entangled with a B tilde because, well, B is entangled with whatever R is entangled with which is L. And in particular, it's entangled with a bit some mode of L or some bit of L, which we call LB. Now, if you knew that the state is in the thermal field double, which is some e to the minus beta e over 2 e, then you know that you can continue this diagram to get something like this. And what B tilde is it's nothing other than the future sort of propagation of LB. And so this is an example where you have a black hole, at least from the right perspective, is entangled with another black hole, but there's no issue with monogamy because B tilde is identified with the mode that is entangled with B. And so, so B tilde is equal to LB, and so there's no contradiction with S B tilde B equals S LB B equals 0. You can also consider you can do this in flat space. So in flat space, you can if you have flat space with a strong magnetic field, then you can pair create such black holes. So the space-time looks something like this.
Sorry, I think it's better to say that PT is in the future of LB rather than to say that someone who falls from the right cannot change LB.
But in the situation where you know that you're not going to add anything from the right, then I think there is a one-to-one correspondence between things here and things there. That's how I was thinking about it. But yeah, maybe the more careful thing to say is that the subsystem which purifies B is in the future of LB, so there is some dependence between things that you can do on L and the interior.
You said this is true in free field theory, interactions, their expressions.
Sure. So now you can consider, as I said, flat space plus magnetic field, in which you can have pairs of black holes that can just be created from the vacuum in precisely the thermal field double state. So you can have a black hole there and a black hole there, L, R, and they're entangled, as I said, in the thermal field double. So mode B here is entangled with some, well, it needs to be entangled with B tilde to have smooth infall here. But it also is entangled to some subsystem LB of L. And there's no contradiction because you have this wormhole. And the idea that you should think of B tilde as some subsystem of L, and therefore there's no monogamy paradox. Now, one thing you can do well, you can draw very nice diagrams, which I'm going to attempt. You can now, so this is not an evaporating black well, it's going to evaporate. So to get something analogous to having a black hole maximally entangled with Hawking radiation, is that you can put one of these black holes, let's say the right one, inside some sort of Dyson sphere that reflects all the radiation inwards, and you can let L evaporate. Then you're going to get this awesome diagram. I'm going to attempt to draw this. You have these Hawking modes. So the L black hole has evaporated. Oh. And so you get the flying spaghetti monster. So this is R. And again, the idea is that B needs to be entangled with B tilde, but B tilde is secretly encoded in all the radiation. So there's some LB in the radiation, which should be thought of as B tilde. Okay? Now you might be worried that maybe this thing is a, oh, any questions about my awesome artistic skills? No? Okay. You might say that maybe this is a mechanism for the firewall. For example, as these modes LB propagate in the space-time, they might, bump into a dust particle. And maybe that interaction somehow inserts a shock wave or some excitation that now becomes sort of localized just behind the horizon. The argument for why this won't happen is sort of intuition built from this state, from the thermophile double. You should think of the state of the two black holes there, or in this case, where you let one of them evaporate, as a state close to the thermophile double at t equals 0. Sure, you can move one of them maybe up a little bit or down a little bit. That's fine. And you can model. So now the idea is that this interaction with the environment is in some sense a simple interaction. It's sort of a local interaction that happens between one Hawking mode and one dust particle and so on. And therefore, you expect that is dual to acting with a shock wave operator somewhere here at near t equals 0. And what that does is that it inserts some excitation this way. So anything simple you do, so that's the point, anything simple you do in this region will always have this interpretation, something falling into the black hole from t equals 0, therefore not affecting the vacuum nature of the horizon over here. Now you might say, but what if I measure all of the bits? I just, by measure I mean, let's say all the bits interact with dust particles. Well, even if you do that, provided that the full projection operator that you act with, well, the measurement on all the bits is not too complicated, that also has the same dual. It does something over here. This is motivated by recent work of Juan and Iwana, where in the context of the SYK model, you can act with a full projection operator on the thermophile double on the left CFT, and what that is dual to is that it inserts an end-of-the-world brane very far away from the bifurcation surface, which falls into the black hole. And therefore, even a complete measurement on the left CFT is not going to affect what you do here. There exists, however, a class of projection operators that are very fine-tuned, or a class of measurements that you can do that are very fine-tuned that can affect things here. In particular, you can time evolve backwards for a very large amount of time, and then insert a shock wave. And what that's going to do is that it's going to appear just behind the horizon. But this amount of time evolution that the operator undergoes here is a proxy for how complicated the operator is. And the more time evolution you need to do, the more complicated. And therefore, you need to do something very hard on the Hawking radiation to form the firewall, or something that looks like a firewall. And therefore, this proposal has sort of built into it a mechanism, sort of a safeguard for being protected against forming firewalls. Let's see, anything else I want to say here? Yeah, I think that's all I had. Any questions about this? Yes? Raise your voice.
The statement of typicality that we derived earlier, is that it's saying it's supposed to operate with different complex?
No, so I mean here, there was no analogous condition. So here we're assuming new physics. And I think really that's the attitude that one should take from the firewall. It's not that there is a firewall, but that there's new physics waiting to be discovered, or maybe already has been, and to put more equations into the picture. Let me stop there. Thank you. Questions? Yes? Oh, you're asking about the nature of these wormholes?
No. Yeah,
I really have no idea. These wormholes are not, no. But that wormhole can be traversable. I mean, I don't understand what these wormholes are from a quantum gravity perspective, but I mean, it's just a natural thing to expect from this diagram. If you let this thing evaporate, well, there must be some channel in which these bits can affect the interior. But so far, this is just a picture. Yes?
So suppose you let your radiation interact with some ancillas that you initialize to some fixed state 0, so that you swell the quantum information for every single one of them. Would you say, like, even in that case, you don't have a firewall?
You don't have. Depends on the interaction that occurs between your ancilla and the bits. If it's something like I described here, something simple, then I would expect there not to be a firewall. Yeah. Unless, Juan, if you have a comment about that? Yeah?
Can you explain to what extent you think this is the same or different from state dependence?
Yeah, so at least in the context, well, so something I've been talking about for a while now is in the context of the SYK model. As I said, you can, there exists an entire basis of projection operators in some special basis where if you act with P, so this is the projection operator on the left, if you acted on the thermal field double, left, right, so this produces for you a state psi, which depends on P, of the right. Okay, so that's just obvious. For a class of for a certain class of projections, all that does is that it inserts an end-of-the-world brane, as shown, and does not affect the physics here by much. It does affect correlation functions slightly, but it does not create a firewall. Now you can show that you can use a sort of quantum error correction and so on, and you can actually write down what, well, not the operators here, but the operators here. You can establish the dictionary between operators here and the right-hand side. So you can actually get a dictionary for operators behind the black hole horizon. Notice these were outside the black hole horizon before the projector, but after acting with the projector, there's an end of the world brane, and everything needs to be mapped to the right-hand side. And in this model, these operators depend on which projection operator you acted with. And I think, if I recall correctly, it's clear that it's not a linear operator that you can define in terms of projectors on the right, they project on a state and use an operator and so on.
So you say it is state dependent.
It is state dependent. Yeah, yeah.